All right, so I'm going to go through these posters. I think these posters are a pretty good checklist and pretty comprehensive of the knowledge that you need to go through this unit, Unit 7. Right? Again, this is the last unit that we're reviewing right here. Right, so one thing is that rotational analogs. So everything that you guys learned in linear motion, there's some kind of rotational equivalent of that, some kind of rotational analog. And sometimes I've seen even AP ask a question like, what is the linear analogy to this rotational situation? I think AP Classroom, the one's coming up, that question shows up. Right. So here, I'll give the first one to you. Right. So time is still time. Right. That's the same. Right. So however many seconds are taken away, seconds are still taken away. Right. Now, these first few variables are going to be kinematic. Right. So we're not looking at forces or torques or anything like that. We're just looking at straight motion. Right. So x in meters. Right? So now this is linear motion. Everything the left column is linear motion. So if you just like walk forward or forward and backward, right, it'd be like, what's your displacement? Right. Displacement, right? In meters. Right. What here, you guys got your notes out? So as you're going along, write down on paper with your hands, right? Because this is the thing too. I mean, I've learned this over the years. You guys probably have now too, since you're like at the end of high school. If you can write down on paper, then that for sure confirms that you know it in your mind, right? And if you can't, you think it is, and then you see the answer, then your brain does this whole confirmation bias thing. It tricks you into thinking that you knew something you didn't. Okay? Right. So who can tell me what is the rotational equivalent to displacement? Yeah, radians is the measurement, right? So angular displacement. And what's the symbol for that? Theta. Exactly. Yeah. So you guys wrote theta is the symbol, and then radians is the unit. Okay. Okay. Now it's a good time to break out this turntable. Right. So let's take a look here. Right. See this thing rotating, right? And so I can see like how far does it rotate? Right? You could quantify it different ways. You could quantify how many degrees does it turn. You could quantify how many revolutions. But the best way is radians because radians fit straight into the equations. It's a certain equation we're going to come across. Right? Right. Now, okay. Next one, we could do v velocity, like meters per second. Right? And what's the rotational equivalent to that? Angular velocity. What's the symbol for angular velocity? Omega. And the unit is
Radians per second.
Boom, radians per second, right? Like that, right? So how fast is this turning, right? Not how far is it turned, but how fast is it rotating, right? Like for example, the Earth rotates one revolution every 24 hours, right? You could convert that to radians per second, right? Just a unit conversion, right? Right. Acceleration, meters per second squared. Right? Now that's a linear sense. What's the rotational equivalent? Angular acceleration. What's the symbol for that? Alpha. Boom. That'd be like, ooh, radians per second squared. Okay? So that's like now if I have my turntable like speeding up faster, 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 right? How can I quantify it faster, faster, faster? Or if I let it go, there's a frictional torque on it that brings it to a stop. What's the rate of slowing down? Oh yeah. Uh, okay. So they're different units. Oh yeah. Okay. Right. So right, acceleration is meters per second squared. That's like forwards and backwards, speeding up, slowing down. Alpha is radians per second squared. That's like turning faster or slower. Okay. Right. The rate that you're speeding up, slowing down. Okay. All right, you guys good so far? Right now, those are the kinematic variables, right? Then switches over to like dynamics. We're going to start bringing in like inertia and force, torque, that sort of thing, right? Right. So when we were doing linear motion, we were talking about mass, right, measured in kilograms, okay? And that represented how much inertia something had. You guys remember like Newton's second law of motion, put a force on something, right? The more mass it has, the less responsible, or well, right, the less it will accelerate. Right? Okay. What is the rotational equivalent? Rotational inertia. Exactly, rotational inertia. Also called moment of inertia. If you ever see that term, it's the same idea. Right? And what's the symbol for that? I. Exactly, capital I. Right? Capital I. Right? Okay, guys, a little expression here. The sum of them are squared. Okay? So if there's like now this could be referred to a single point. Here. So if I know what the mass of this point is right here, right? And I know this radial size right here, right? So here, if I break out a ruler and say, how many centimeters, I quantify how many meters is it right? From here to here, right? As it's rotating, right? There's some inertia it has. Right? If I slide it around, right? Like near the middle, it has hardly any inertia at all. Okay, it's really easy to rotate that. But the further I move it out, I guess it's more obvious if I use a big mass, right? Like here's 1 kilogram. Okay, it's really easy to turn. But if I move it way out here, ooh, now I feel a lot more resistive force to getting it to move. Okay, so mr squared. Right. And then if you have a complex object, you add up all the points. That's what the sigma's about. Okay. Newton's second law of motion. A lot of times I like to say acceleration is force on mass. You see it this way too. F equals ma. What is the rotational equivalent to that? Yeah, Leonard?
Linear.
Yeah. I could think of it that way. Mass is like linear inertia. Yeah. Okay. Now, I'm glad you asked that because here, it's a good point to make too. Sometimes AP will ask this. Mass has 2 main properties by AP's book. 2 main properties of mass. One is inertia, right? So more, okay. The more mass, the less it wants to accelerate for some force. The other property of mass is that it gravitationally attracts. Okay, so they'll call that inertial mass and gravitational mass. Okay, right. So if you ever come across that, you're like, okay, break out those terms: inertial mass, gravitational mass. You guys can do that. Okay. Right. So what is the rotational equivalent to Newton's second law of motion? Torque. Right. Instead of force, now we care about torque. Right. And what is torque? Radius times force. Yeah. And there is another expression for torque too. Torque is also equal to
Angular acceleration.
boom. Rotational inertia times angular acceleration, I times alpha. Okay. So R cross F, this is a cross product here, but it's also I times alpha, right? I'd like to run through an example specifically. Actually, let's do that. Let's take this. Right. Let's say I have a turntable, right? And it can spin about this central axis right here, and spin, rotate, right? And I wind a string around, zoom. Now it's got a string around this. Okay? And I'm gonna pull with some tension force. I'll call it F sub T, some tension force, right? And I know, let's say I know the radius of this thing. So I'll call that R for radius, right? And if you know the mass of this thing and how the mass is distributed and how big it is, blah, 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 right? You can figure out its rotational inertia. Usually AP will give you the rotational inertia. So I'll just call it I. But you guys know that the mass, the radius, the fact that it's a flat disk has something to do with mr squared. Actually, if it's a true cylinder like that, it'd be 1/2 mr squared. But that aside, let's say you have that I, right? And you want to know, what is the rate? Actually, I've got the spinning the opposite direction I'm pulling. Maybe it'd be slowing down. Wouldn't that be true? I didn't mean to do that. But if it's rotating counterclockwise and you're pulling in a way that would cause it to go clockwise, it would have to slow down, right? So I could say, what is the rate that this is slowing down? Okay. At what rate does I'll call this like omega naught, maybe, does the turntable slow down? Right? See if you guys can solve that. Come up with some expression based on what I've given you guys right there. Okay. What rate does it slow down? Okay. Suppose you have given values for all those things. You know omega naught, you know I, you know R, you know the tension force. Maybe they give you numbers for those things, but I'll just leave them as variables and see if you guys can come up with an expression in terms of those variables that would answer that question so that you could just plug in the numbers that they give you and it would lead to the straight answer. Straight to the answer. All right, who's got the answer? Who's got the answer? Yeah, what you got, Scott? Exactly. All right. Did you guys get what Scarlett got? Here, I'll walk you guys through the solution and lead exactly to what she said. Okay. So we're using like this, like Newton's second law of motion in a sense, but in a rotational context. I'm going to say, well, torque is equal to I times alpha, or if you like, alpha is equal to torque divided by I. Hey, that's analogous to A equals F over M, right? So same idea. Right? Oh, but what is torque? I know that torque is equal to R cross F. Right? Oh, and look, I gave you those things, the R and the F. So that's it. The rate that it's changing its velocity, which in this case it would be slowing down because it's being pulled the opposite way that's initially moving, right? Would have to be r cross f divided by I. Right? In fact, if you want to throw a negative sign on that, then maybe that would be a good thing to consider too. The fact that these would have opposite signs, right? So sometimes AP likes to do that. They like to say, like, do you recognize that it's that the initial angular velocity and the acceleration have opposite signs, right? Okay. Right. Guys, go there. Just do that. All right. Next on the list here. Ooh, momentum is mass times velocity, and that's in a linear sense. Right? Some mass, some velocity, multiply it, it's got some momentum. Right? What is, oh, guys, momentum is mass times velocity. Is that a scalar quantity or a vector quantity?
Vector.
Vector, right? And that's a really important detail because now you have to know, say if there's a head-on collision, if someone's going to the right, someone's going to the left, that they have opposite momentum. So sometimes they'll even cancel out. You have something moving really massive, really fast to the right, really massive, really fast to the left. It might be zero momentum in the system because it just subtracts, right? It could be, okay. What is the rotational equivalent of that? Angular momentum. What's the symbol for that? L, capital L, right? Capital L, right? And capital L is equal to what times what? Is that what you just wrote? What Leonardo said? I times omega? I times omega? Right? I times omega, right? Sometimes they throw a delta in here, like if it's a changing angular momentum, but here, right, the example we were just looking at, if this thing is changing its, how fast it's rotating, right? Then it'd also be changing its angular momentum, right? So you might be like delta L equals I times delta omega, okay? You're changing. Ooh, kinetic energy is 1/2 mv squared, right? Now, is that a scalar or a vector quantity? That is a scalar, right? So you don't care about signs or directions, nothing like that. All you care about is just the magnitudes, right? Okay. So that's a scalar quantity. Right? What is the rotational equivalent to kinetic energy? Boom, 1/2 I omega squared. Right? You guys see if you just like pop in the analogous parts, you get completely valid formula too, right? So maybe this turntable rotating, whichever way it's rotating at some point, has some energy that's associated with that rotation, and you can quantify it like this. Okay, guys, good. Good. Right. All right. So here's a kickstart right there. All right, are we good? All right. Let's do. Right. Here's some rotational inertia table. I want to walk you guys through this real fast, but not spend too much time again. Because again, AP will usually tell you like some value of a rotational inertia. And sometimes they even see them like make some kind of weird quirky mistake, but that's not right. So if it's a single point, like if you have a single point like orbiting around some axis, it's mr squared. Okay? If it's a ring that's also rotating about its center, because you have to know the axis is rotating about too, right? Well, that's essentially just a bunch of points, so it's going to be no different. Okay? Now, if some of the mass is distributed closer to the center, actually the solid cylinder looks pretty close to this turntable. It's pretty close, isn't it? It's an octagon, right? Right. Then it's got to have, well, some of its mass is closer in, so it's going to be less than mr squared. So it ends up being 1/2 mr squared. A coin spinning about its edge, pretty close to that. Right. You got these other values, right? Okay. You guys good there? All right. Parallel axis theorem, same thing. Just want to take us through this real fast. AP is not going to ask about this. AP just does clockwise, counterclockwise. That's really all they care about. Is something rotating clockwise or counterclockwise, right? Now, there's some reasons, or I'm sorry, am I thinking something different? I am, never mind. Oops, I'm thinking right-hand rule. Oops, get ahead of myself. It's practice on this weekend, but yeah, okay. AP's not gonna ask about this, but if you take physics in college, then there's a really good chance you're gonna see this, right? So, right, like if you have like some shape and it's also like located so far out, then you can say what its rotational inertia should be about its own central axis according to that last table, right? And then just like add another mv squared where d is the distance that's removed. Okay, so let's move on from there. Oh, okay, here's one that I wanted to ask you guys about, right? Torque. Right? You guys already told me this. Torque is r cross f. Torque is also equal to I times alpha. Right? In fact, you can put those two ideas together sometimes you can say r cross f equals I times alpha. And you can solve for, actually, that's what we just did as an example of the turntable, right? Isn't that exactly what we just did right here? Torque is I times alpha, torque is r cross f, put it all together, boom, solve for stuff, solve for alpha in that case, right? So remember, a cross product means that you are only multiplying together the perpendicular components, right? So every time you turn a wrench, open a door, those are examples of this turning moment. Okay? So if I have like this radial distance from this pivot point, right, and some force that's applied, and here's the angle between the two, right, we do like that. And I only care about the perpendicular component. Right? So like if you push or pull like parallel to the door, that's never going to turn the door or the wrench in this case. Okay. All right. So we got next here. Okay. So this next one is right hand rule. Okay, here's another one that, okay, this is what I was trying to say when I was saying AP cares about clockwise, counterclockwise. So something rotating clockwise or counterclockwise. That's as much as you have to know for AP. Okay. When you go to college, there's a really good chance they're going to mention this. And this is kind of like an upgraded version of that. Okay. There's more you can do mathematically with this. There's some reasons this is a better framing, but it's a little bit more abstract. So I just want to give you guys exposure, say, okay, this is here. It's like if you turn that door right there in the XY plane, just clockwise or counterclockwise, torque is actually defined along the z-axis. There's good reasons for that. It's kind of an abstract idea. Okay. Okay. All right, let's look at equilibrium here. Okay. So maybe we've got a point and I want to put it in some kind of equilibrium, right? Okay. Can you guys write down on your paper what some conditions for equilibrium might be? Conditions for equilibrium. Right. Write down all the conditions that you can think. Okay. What would put something in equilibrium? Give you guys a hint. We talked about equilibrium way back in probably unit 2 dynamics. But there's a reason I'm asking it with rotation too, because there was, we waited many months and then we finally added on one more rotational detail at the end. All right. Did you guys say, here, show you the answer here, right? That if you're talking about 2D equilibrium, so we're just talking about like maybe like an XY plane, just something like this, right? The sum of the forces have to go to 0, right? And also the sum of the torque goes to 0, okay? Now, you guys remember like vectors and vector components. So one thing that's really common to do is to introduce a Cartesian system and break vectors into components, okay? And if you do that, then in the X plane and also in the Y plane, everything has to 0 out, okay? And then for torque, again, if you just talk about an XY plane, torque, if you follow that right-hand rule, it would just be perpendicular to that. AP is not going to throw in the subscript C, but they would just say clockwise or counterclockwise, right? There would also have to be no net torque. Okay? Okay. Now, if you take this into 3 dimensions, again, some of you guys might take physics at college, or if you do engineering classes, you're going to have to think about building structures that are in 3 dimensions, and you have to satisfy actually all these conditions. So the forces 0 out along 3 axes, and same is true for the torques. Okay, Richard? Okay. Let's do, here, I've got a good example that's lined up. Here's an AP style question. I've seen them ask things like this. There might be one of these on your AP classroom that you have to do. It's a good chance to be asked something like this on the AP exam. You guys try kind of a simple one here. Right. Let's say there are equal spacings here. So these are all equally spaced. Okay. Maybe I've got all right, so I see that. And I'm going to put some forces on these. All right, so let's have let's go 20 newtons. What's that there? Centimeters, right? Good practice. 10 newtons. And 20 newtons. Okay, so you have that, and that there's a pivot. We'll define this as a pivot. Now, you might remember back when we did the lab version of this, you could technically pick any point anywhere and like sum the torque about it and zeros out. But sometimes there's like an extra convenient point, right? Usually where there's a force that you don't so much care about considering, right? Like where we literally pivot about, right? Maybe like the door hinge or the nut that a wrench is like turning, something like that. Right? So the question might be like, where could you put a fourth force and how big would that force be so that the so that it went into equilibrium, right? And they might give like some kind of multiple choice version of this, but can you guys figure that out just like on your own paper? Like if you were to draw a fourth force that balanced everything out so that everything was in equilibrium, where would you put that fourth force? How large would it be? Guys, a moment, think about that. Where would you put a fourth force? And how large would it be so that everything balanced out? All right, and what do you guys come up with? Who thinks they know? What do you think, Elijah?
Second unit across, 10 newtons downward.
Boom, boom. All right, you guys got Elijah got right. Second unit across, 10 newtons downward. Do 10 newtons right here. A lot of times AP likes to do, again, I've seen asked this type of question a few times in the past, and many times there's some kind of symmetry that pops out of it. Like, yeah, try to give you guys kind of a basic example, and this one is that there's symmetry. You see that? Okay. Now there is a fifth force on here. Where is the fifth force, and how large is the fifth force?
Center point, 16.
Boom, center point, 60 newtons up. So it's like 60 newtons up right there, right? Right. And now we've satisfied all the conditions. I can say the sum of the forces, and I'll just say the y direction is 0, like 0 newtons, because I don't really care about x direction forces in this case. That's just 0 anyway. Okay? But also the sum of the torque. I'll just say torque, although it's torque out of the page, but whatever. 0 Newton meters. Okay. Guess that. Okay. So 60 newtons up, 60 newtons down, satisfies that. Okay. And then suppose you pick this pivot point. Okay. You're looking at like 10 newtons times 1 unit, 20 units times 2 units. What would that be? 10 times 1 is 10, 20 times 2 is 40. So would that be 50 units saying, let's go counterclockwise? You see that? 40 plus 10 would be 50. Right here, throw in some numbers for distances. Let's call this 1 meter here. Let's say it's all the way 2 meter marked that way. And then the same thing here. Got 1 meter here, then 2 meters all the way out here. Right? Let me sure. Okay. And then and then there would be another 10 plus 20, or, sorry, 10 plus 40 would be 50 Newton meters saying, no, let's go clockwise. And then those would all cancel out. Okay. All right. Ooh, actually, speaking of which, that's here's a slightly more complex example of the same idea. Okay. So, did I tell you guys the story with Paul Hewitt walking around the scaffolding? Like that? Yeah. Okay. So he worked a bunch of odd jobs. You guys know Paul Hewitt, the guy that has demos that I like to show you guys sometimes when I can. By the way, he's got some really good ones on electricity that I want to show you guys, but I cut a bunch of stuff for time, so you have a chance to watch my honors videos. They're there if you want to learn about circuits. Okay. So he was a sign painter at one time. He's walking around on scaffolding. He's thinking, like he and his buddy were thinking, what about the tensions in these ropes? I guess if we walk closer to one rope, the tension on that side is going to go up, and the tension on the other one would go down. They were like plucking them and like listening to them and thinking about this. They're trying to figure out what exactly is this relationship, or like how would you figure out exactly what is a tension, okay? And do the tensions up always equal the forces down, which you guys know they do. Right, so here's like a broader expression you could do. Right? So the sum of the forces goes to 0. I'd say, okay, these two forces up, boom, minus these two forces down, boom, has to 0 out in terms of newtons per force. Okay? That's actually from unit 2, straight from unit 2 dynamics. Okay? The unit 7 rotational dynamics application is this torque application. Okay? Now this one, remember, you're allowed to pick any point as the pivot point. Looks like the way I set it up here is I chose this point as the pivot point. Okay, now if you do that, whatever force is at that point causes 0 torque at that point because it's 0 meters away. It's kind of like if you're pushing directly on the nut, you have a wrench, then that's never going to turn the nut, right? Makes sense. You have to like pull out on the handle. Right? We got the weight of the beam at L/2. Right? That's a common thing to do. Even though the weight of the beam is distributed, right? You can treat it as a single point at the center of mass, and mathematically it works out fine. Right? Good chance you're going to see and have to apply something like this in college. You have to figure that out. That, oh yeah, it's a uniformly distributed beam. Its center mass would be at the L/2 point. Okay, right, so look for that in college if you're taking physics. Okay? The weight of the apple at some location X. You call this X, right? Okay. And then finally, the tension on the right side pulling at the full length of the beam. That would all zero out, wouldn't it? Okay. And it looks like if I was looking at calling something clockwise, I called it negative, negative. These two saying, let's turn this whole thing clockwise, negative, negative. Okay. But then this tension over here is pulling back counterclockwise, so I call it positive. Right? Right? That all right? That's good. Okay. So this next one is a really important one. Don't want to reveal it yet. I want to draw a couple of, well, let's draw paragraphs here. Pair of graphs. So one concept that we've talked about is torque, which is measured in Newton meters. Okay. Let's do that as a function of time, say in seconds. Okay. Another concept we've talked about, and make sure this is going to match my, yeah, right. Is angular momentum. Right. Now, this one, you could define it in Newton meter seconds. You could define it in, say, m squared. That'd be kilogram meter squared. Yeah. Okay. Right. So, but both of those are equivalent. Okay? And let's do it also as a function of time in seconds. Okay. Now, here's the scenario. Let's go back to this guy right here. This guy right here. Okay. Let's say that this actually starts from rest. Let's say omega naught is equal to 0 radians per second, which means, of course, it's going to eventually just start going around clockwise, right? Because you're pulling in such a way that would force it to go clockwise. Right? So let's say omega naught is 0 radians per second, starts from rest. Okay? And then I apply a constant force at a constant radius. Right? And this thing speeds up spinning. I see that? Right. Draw the two graphs on those sets of axes that correspond to that story I just told you. Right? Take a trip around the room and see what's doing here. Who's gonna get this? Okay. Say it again. So I've got that turntable. I wrapped a string around the edge. I'm pulling with a constant force at that constant radius, and it's speeding up spinning. All right. Yeah. Victoria's got it. That's it. That's a winner right there. Who else is going to get this? Yeah, Scarlett's got it. Winner. Uh, ooh. Leonardo got it. Gabriel got it. Sienna got it. All right, Elijah got it. Oh, I think Michael got it. Yeah, Nicholas got it. All right. If I missed you, sorry, I may have missed a couple of guys, but okay. So okay, say that one more time, and then I'll show you guys the correct answer. A bunch of you guys got it. That's awesome. Okay. So guys, if I'm applying a constant force at a constant radius, that's called a constant torque, isn't it? Maybe there's like a right angle here. You're thinking 3 dimensions, right? Okay. That's a constant torque. Okay. Well, if it's a constant torque, that's like this right here, right? There's your R cross F. Okay. So time's ticking along, tick, 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 right? I'm just pulling with a constant torque. Tick, 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 tick. Right? And what's happening to the angular momentum? Right? Well, so you guys remember torque is R cross F. Every component there was constant, the whole thing's constant. Okay? But angular momentum, what is angular momentum again? What times what? Yeah, there you go. I times omega, rotational inertia times angular velocity, right? And is rotational inertia constant? Yeah, that'll be constant, especially if they say the string has negligible mass. Right now, if they say the string has mass, then it's decreasing a little bit. But if the string's negligible mass, that's constant. But that angular velocity, that's increasing. In fact, that should be increasing at a constant rate because the torque is constant, and torque is equal to I times alpha. I is constant again, right? Which means that alpha would be constant, right? And if alpha is constant, then omega versus t has got to be linear. Therefore, this is also linear. Okay. So, and I have the starting at rest. That's the last detail. Is if it starts from rest, then this point would be 0. Okay. So then, right? So this pair of graphs right here, guys, your Unit 7 AP classroom, some of you guys have done it already, and you know that this pair of graphs side by side is going to help you out with a number of those questions. This comes up quite a few times. Okay? AP really cares about this concept. Okay? And if you haven't done it yet, then definitely hold on this page of your notes and think deeply about this because it'll help you figure out a bunch of those questions. Okay? Right? Now, what if I go back and change some things? Because originally I had this rotating in the clockwise direction and I'm pulling counterclockwise. Okay. How would that change this graph if it was originally rotating backwards? Could you take this whole line, just shift it straight down, right? Right? Because it would have a negative angular velocity to start with because it's going the backwards direction. Okay. And then at some point it's going to slow down and come to rest for like 1 instant and then turn around and start speeding up the other way. And at this point right here would be like where it came to a brief stop. Right? And when I say stop, it's sort of analogous to if you throw a baseball straight up in the air, it has 0 velocity at the very top, right? It's only for like 1 moment. Right? Okay. And if it was already spinning and you in the positive direction and you're applying a positive torque, then maybe you can move the line up here. Right? Okay. Let's get that. Okay. So here, what is another connection between these two? What is the slope of this line equal to? I'll give you guys a hint. Okay, guys, if you're ever trying to interpret a graph and figure out, what property of the graph represents what thing? Okay, obviously, every coordinate represents angular momentum, right? That's what the graph is. Okay? If you're interested in slope, guys, is slope rise over run? Right? Now, rise over run, is that, can you just do that with the units also? Like, look, I gave you guys Newton meter seconds here and seconds here. Okay? What is Newton meter seconds divided by seconds? Yeah, the seconds cancels and it gives you Newton meters. Right? Oh, Newton meters, what does that describe? A torque. Right? In fact, is this a constant slope? Just like torque is a constant value. Look at that, right? See how it goes hand in hand, right? Oh, yeah, thanks, Scott. But if there's a property of this graph that represents something about this, could you go the other way too? Right? What property of this graph tells you something about angular momentum? The area under the curve. Okay? I'll call it like the change in angular momentum. Okay, so I'll call this delta L. Delta L. Can that be true? Like you're changing angular momentum, right? Which makes sense to you. Like here, even if you shifted this line like down or up, say like it had a different initial starting value, the change, like the vertical change, would still be the same. Like this graph could still be the same. Like, I could move this torque, or sorry, the angular momentum line up or down, and the torque graph would still look the same. Okay, right? Guys get that? Right. All right, so let's look at the poster version of that. Okay, that was this right here. So if you put it all together, then that's what you got, right? This, know this, know this. You're going to get a few questions of this on the AP exam in a few weeks here. Okay, and I just walked you guys through the whole process. Okay, right? And yeah, you guys got some good practice problems on AP Classroom to acknowledge on that. Ooh, all right. This next one. Okay, this one I like a lot. This is actually pretty similar thought process to uh, this. So the turntable, it's like I was applying a force, some radius, so that's a torque, yada yada. Okay. But let's go an extra step and say, here, let me have to solve for this. Okay. Oh, how fast is it spinning after some given time? Right? Give you guys sort of a hint, one way to think about it. I mean, if you have a turntable or a basketball, there's different shapes, right? Right? It's how fast it's spinning after some time. As far as we went with this so far today, is I said, like, what's the rate that it's speeding up spinning? We came up with alpha as some expression. If you know that you can plug it in and know the rate that it's speeding up spinning. If you want to know how fast it's spinning at some particular time, don't you also have to know what one other thing? How much time has passed, right? I've been pulling for 3 seconds, 5 seconds, 10 seconds, right? The longer I pull for, right? The longer you apply this force for, right? Right? So let's say you got the basketball on your finger and you go to flick, bam, right? Maybe you apply this force for like half a second, right? And you know all these things. Okay. How fast is it rotating? Now, one way you could do it is you could solve for alpha first and then go skip over to rotational kinematic and solve in terms of time. You could do that. But you could also solve this in terms of, well, okay, here. But could you also combine it with, say, like this graph right here? It's like if I know the torque and I know how much time, I could just skip to that and do angular momentum, which is I times omega. And then if I know I could solve for omega, right? Okay, tell you what, since we're here, a little short on time here, I'm just going to walk through this process, show you guys what I got here. Okay. This is one way to solve it, not the only way. Torque times time interval is change in angular momentum. Oh, isn't that exactly pairs with this graph? Right, I mean, again, it's just one way to do it. If I know the torque, right? Oh, and let's see, what is torque? Well, that torque is this R cross F. If I know R and F, you cross those, right? The time interval, again, might be like half a second that you apply that force for. It's like, right? And if I only know the rotational inertia of the basketball, I can know how fast it would be spinning at the end of that interval. Oh, well, that's where you pull up this rotational inertia table. I know a hollow sphere is like 2/3 mr squared. Again, AP would give that to you. They wouldn't expect you to memorize that at all. Okay. So I could plug in 2/3 mr squared, right? Right. And then, okay, and then you can solve it from there. This was a previous quiz question. I do remember asking guys this on a quiz, right? So you guys seen this before? You know how to do that? Right. Right. How about like an ice skater type situation, right? Now, if the ice skater is basically a closed system, or you treat her as a closed system, right? Now, maybe you could say, well, she has a weight and a normal force, but those are going to balance out anyway, right? Right. But she like, goes into a spin, she pulls her arms in, she's going to spin faster, 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 right? Right. Now, the physics of this is what do you know about angular momentum? It's conserved, isn't it? Is angular momentum conserved? Conservation of angular momentum, right? So as I times omega has to be conserved. Oh, that's this right here. This is conservation of angular momentum. Okay. I times omega is conserved. So if you have your arms extended out, that's a huge mr squared. Right? Now, even though her mass doesn't change, her distribution of her mass does. So she pulls her arms in, that average radial size changes. Right. So the I value goes down, which forces the angular momentum to increase. Right? Angular momentum, is angular momentum a scalar or a vector? The vector, right? So directions matter. And as far as AP cares, they just say clockwise or counterclockwise. Okay. Right. Okay. Ooh. Okay. Now this next one, here, I'll show you guys the title. Angular momentum for a point mass. Here. It's this. Angular momentum for a point mass. So there's a really good chance that this is going to be a couple of questions on the AP exam. Okay. What if you have like a swivel stick and it's just like hanging out here? Here's the point that it could swivel about, possibly. And you take a ball of clay, and the ball of clay comes in and sticks to it right here. Okay? So the clay has some mass, the clay has some initial velocity, and this stick has some, let's say some rotational inertia, I'll call it I sub S, and it has some length, I'll call L, and the point that everything happened, bam, this collision, I'll call that point, I'll call that distance X. How about that? X. Okay. So is this thing it's gonna rotate with some omega, isn't it? Right? After it sticks and starts rotating. Right? So like, how would you even start to approach that problem? Right? You can actually do it through conservation of momentum, conservation of angular momentum. Right? Now it starts out like nothing's rotating, right? There's just straight line motion. Okay? But then it starts rotating after that. But angular momentum is conserved, just like regular momentum is. So in a sense, you could always define some kind of angular momentum in the system, even when the clay was just coming in a straight line, right? Sure. Right. So here, what I would say is, whoops. Oh man, I meant to ask you guys this. Right. The angular momentum of a point mass. Right. Guys, you either had to know this or if you didn't know this right here, then make sure this is in your notes because this is going to show up. Okay? MVR. So it's just the regular momentum of the point mass times the radial distance that it strikes at, right? Which for me would be x, right? I don't really care about this L. All I care about is this x, okay? I've seen AP ask that too. So does the L matter or does the x matter? Oh, the x matters. Right? So MVX. Because what if the apple like hit at the pivot point? It wouldn't rotate at all, right? So they're, okay. You guys can do that? Right. So like MVR, where R is the place where it sticks. Right? And sometimes it'll bounce off too, right? All right. How about a ball rolling down an incline? Pick a basketball. Right? I've got a couple of slides for this, different points of view. Now, I doubt AP would ask something where you had to directly apply exactly this, although maybe some parts of this, maybe. Know this, be able to say, okay, free body diagram. There's the way the basketball is acting through its center, you can treat it like that. The normal force actually acts at this point on the surface, and the friction force also acts at the surface. Now that's different locations that those forces act, which sets up a torque, right? Right. Okay, so you can go through dynamics, rotational dynamics, and figure out how fast it's moving at the bottom. If there's anything they want you to, here, tomorrow, one thing you'll have to know is the other way I'll have you approach this, which I think is a little bit easier way, which is conservation of energy. Okay, so I've got the same scenario. I want to know how fast the basketball is spinning at the bottom. The solution is this how fast the basketball moving at the bottom. That's the answer. But there's, I think, an easier way, more straightforward way to get to the answer. Conservation of angular, or sorry, conservation of energy. Okay, conservation of energy. Energy is a scalar. You guys told me that earlier. Okay. Here, since the bell's about to ring, I'll show you guys this. It's mgh at the top. At the bottom, it's two kinds of energy it diverts into: linear kinetic and also rotational kinetic. Okay. Right? You guys good there? Okay. Finally, last slide. Different objects. The frictionless hockey puck beats everything. The more rotational inertia it has, the harder it is to get it to rotate. It's going to lose the race. All right, you guys have a great Monday. Tomorrow, I will have a lab set up for you guys involving rotational motion.